Hey kiddos, happy lesson number 2. Today we're going to talk about a few more ideas having to do with momentum. Just so that you know, next class we'll be doing one of our assignments will be a little momentum quiz before we move on to field forces, just so you can check your understanding. All right, so here we go. All right, so today's goals are to be able to describe the 3 common types of collisions in terms of kinetic energy and momentum, and also use force versus time graphs to solve momentum problems. And then finally, we'll use conservation of momentum alongside conservation of energy and projectiles to solve a couple big old problems. Okay, so that we are at the end of mechanics and we're going to incorporate all of these ideas together to solve some problems. All right, here we go. All right, so first we're going to address the difference between momentum and kinetic energy, and under which cases momentum are conserved and under which cases kinetic energy is conserved. All right, so down below we have 3 scenarios. All right, so we've got scenario 1 in this box here. We've got scenario 2 in this box here. And we've got scenario 3 in this box here. Okay, and on the top for each scenario, this is what's going on before the collision, right? Here is before the collision, and here is before the collision. Okay, and then after the collision for each scenario is down below. Okay, so for scenario number 1, we've got the little block has a mass of 8 kilograms and the big block has a mass of 12 kilograms. After they and the little block has an initial velocity of 10 meters per second, and it looks like the big block doesn't have any initial velocity, it's at rest. So after they collide, what we see is that it appears that they have stuck together and they're moving as one unit to the right at a velocity of 4 meters per second. Okay. And what I'm going to ask you to do for each of these scenarios is calculate the total initial and final momentums for each collision. And then in number 2, calculate the total initial and final kinetic energies for each collision and see what happens. Just so that you know, in all 3 scenarios, so for scenario 2 and scenario 3, the little block still has a mass of 8 kilograms, and the big block still has a mass of 12 kilograms. Okay. Scenario, they all start out the same, so in each scenario, there'll be the same amount of initial momentum and the same amount of initial kinetic energy. It's what happens after the collisions that are different. So in scenario 1, after the collision, they collide and stick together. Scenario number 2, after the collision, they collide and they both end up moving in the same direction at different speeds. And in scenario number 3, they collide and they bounce off each other and move at different speeds. And this is just a matter of the bumpers. So scenario number 1 would be like, if you can remember our collision cars when we were in class, this would be the Velcro bumpers where they collide and stick. Scenario number 2 would be if the 2 cars collide and there is no Velcro. They collide, they make some crashing sounds, right? And they physically touch each other. And then scenario number 3, where they bounce off each other, that would be the scenario where the magnetic bumpers were facing each other. They collide without touching each other, and that collision is soundless. Okay. All right, so let's pause the video, and I'm going to ask you to pause as well. And please try and calculate your answers to numbers 1 and 2 for each scenario, please. All right, kiddos, let's see how you did. I just worked out these, and this is what I got. So for the initial momentum in each scenario, we had the 8 kilogram mass, starting out going 10 meters per second. the 12 kilogram mass didn't have any velocity, so it didn't have any momentum. All right, so the initial momentum of the system is just 80 kilograms times meters per second squared. Okay, in scenario number 1, where the two masses collided and stuck together to find their final momentum, we add their total mass. Okay, so the total mass of the two blocks stuck together is 8 plus 12, 20 times 4 is 80 kilograms times meters per second. Okay, so in scenario 1, momentum was conserved. In scenario 2, we've got the 8 kilogram mass going in the same direction it was going, a positive 1 meters per second, plus the 12 kilogram mass was going in that same positive direction at 6 meters per second. So we add together those two momenta of the two blocks. Hey, 80 kilograms times meters per second. So in scenario number 2, momentum is also conserved. And then in scenario 3, we've got our 8 kilogram block going in the opposite direction that it was going initially. It bounced back, and so we give it a negative velocity to indicate it was going in a different direction. So 8 times negative 2 is the momentum of the little block. 12 times 8 is the momentum of the big block. When we combine them, right, a positive momentum and a negative momentum, we get a total momentum that stays 80 kilograms times meters per second. So in all three scenarios, momentum was conserved. But what about the kinetic energy? Okay, so if we look at the kinetic energy of our systems, we've got the initial kinetic energy is just 1/2 mv squared, where the only object that was moving was our 8 kilogram mass, and it was going 10 meters per second. We square that, we get a kinetic energy of 400 joules. All right, in scenario number 1, the final kinetic energy is 1/2 times the total mass, right? Those two moving together at 4 meters per second, and we square it, we get 160 joules. Kinetic energy final, and so kinetic energy is not conserved here. Have we broke a physics law here? Will we go to physics jail? I don't know. Let's figure this out. In scenario number 2, we've got our 8 kilogram mass going 1 meter per second, our 12 kilogram mass going 6 meters per second. If we add up those two kinetic energies, we get a total kinetic energy after the collision of 220. Kinetic energy is still not conserved. All right, and then in our last scenario, we've got our 8 kilogram mass going a negative 2 meters per second. We square that. Our 12 kilogram mass is going 8 meters per second. Square that, and we get a 400 joules of kinetic energy. So it was in the third collision that momentum and kinetic energy were both conserved. And that happens to be in this scenario number 3, where they bounce off each other. And I said that this was the scenario where there are magnetic bumpers. Okay, so does that make sense? Okay, so let's summarize what we're seeing here in each case. So case number 1, we had Velcro bumpers, right? So kinetic energy was lost and the objects stuck together. That means we call that type of collision totally inelastic. So there are 3 types of collisions. One is demonstrated in each of these 3 cases, and I would like to define them for you. So if we say a totally inelastic collision, think of the word elastic, like things that have elasticity are bouncy or stretchy. So if we've got a totally inelastic collision, those two carts are totally not bouncing, so they stuck together. In case number 2, kinetic energy was lost again. The objects collided, but they didn't stick. There wasn't really any bumpers. They just crashed together, right? They made sound, they made heat as a result of their interaction. And so we just call that inelastic, right? There is some bouncing, but not a lot of bouncing. Okay, so that kind is inelastic. And then finally, In case number 3, kinetic energy was conserved. Objects don't stick, they bounce. We call that an elastic collision, right? It's a bouncy collision. And a perfectly elastic collision is when two carts have magnetic bumpers, or another instance in which a collision can happen and there's no interaction between the actual two objects, right? They're not touching, so they don't transfer some of the kinetic energy into heat. And they're not touching, and so they're not going to make any transfer any kinetic energy into sound during the collision. So here's our important statement as a result of this activity: is in collisions, momentum is always conserved, but kinetic energy is not, right? In the instances in which kinetic energy is not, it is turned into heat and sound. Okay, so I would like you guys to pause it now. On the Google Classroom, I've attached a practice sheet called Momentum and Impulse Problem Solving Practice. So take a look at those and see what you can do. One of the last problems I'm going to solve later on in this video. Okay, so give them a shot before you rejoin us, okay? All right, kiddos, so let's move along. If you had any problems with any of those questions, please feel free to shoot me an email, come to your Friday Flex session, or email me and I can send you a link to a special one-on-one conference if you would like that, please. All right, so let's take a look at a force versus time graph and what we can extract from this. This is very similar. We treat this very similarly to how we treated the force versus distance graphs when we were talking about work and energy. This graph is, remember, impulse is a corollary in momentum to the work energy theorem in energy. So if we take a look at this graph, we see a changing force being applied to a mass of 5 kilograms. Okay, it reaches its peak force exerted at 2 seconds, and then it goes back to 0 force after 5 seconds. And if we start from rest, so our V initial is 0, what is the car's speed at 2 seconds and at 5 seconds? Right, so remember, for a constant force, we can say force times time equals mass times change in speed or velocity. That's just our impulse equation. But is this mass experiencing a constant force? No, it's increasing. So we cannot use this equation here. All right, so that's not what we can use in this instance. So instead of force times time, we can say impulse equals mass times change in velocity. And that impulse is the area under this curve. So at 2 seconds, if we wanted to find the impulse that the 5 kilogram mass experienced, we'd have to find the area under the curve. So the area would be 1/2 base, right, which is the time, 2 seconds, times height of 25 newtons. And we get an area of 1/2 of 2 is 1 times 25 is 25 Newton seconds, which is our impulse. Okay, and then we know that impulse, 25, is equal to our mass times our change in velocity, and change is always final minus initial. Right? We know that the initial speed is 0. Okay, so this turns into 25 equals the mass is 5 times V final. Okay, and so that means V final is equal to 5 meters per second. Right, and the final that we were solving for is this is the speed at 2 seconds.